I welcome you all once again to our lecture on Introduction to Machine Learning part 2. This is the 9th lecture of this series. So, here we will be talking about supervised approach again, but now we are talking about the classification. As I have told you, in case of regression, which is also a supervised approach, we did not discuss everything about regression or its extensions to basis function and neural network. Rather, we tried understanding that why to fit a model, how to make it nonlinear, when we try minimizing the error, why to take care of the overfitting problem and how to take care of the overfitting problem considering L2 and L1 norm. So, we also discussed about the model flexibility and interpretability, but in all this one thing was common, that we were trying to predict some continuous variable. In case of classification problem, a classifier is again a function. That time also we were trying to discover a function, but here also we are trying to discover a function which will map the feature space to a label space. Label space in the sense, now our output variable is a qualitative variable which is represented of course in a quantitative term, but it is basically a nominal or ordinal variable. So, for example, we may be determining whether the rating is 1 or 0. In that case, it is a binary classification problem, whether a person will buy an item or not, binary classification. Similarly, the rating can be from 1 to 5. So, in case it is again some kind of categorical variable and they are ordinal in scale. So, first one in this category is the KNN classifier, K nearest neighbor classifier, K nearest neighbor classifier. So, these K nearest neighbor classifiers are the very simple machine learning algorithms and quite widely discussed. So, here this case the model is not built explicitly. Every time a new observation comes with respect to the labeled data set, it has to be found out whether it is closed to the first category or to the second category. So, therefore, every time we have to compute the neighborhood as when a new observation comes in. So, here the idea is, if the record falls in a particular neighborhood where the class label is predominant, it is because the record is likely to belong to that very same class. So, the approach is you find out the k closest points, nearest neighbors from the training record and assign a class level according to the class level of the nearest neighbor. So, if in your vicinity you have 10 points and out of that 7 points are positive class and remaining points are negative, because out of 10 points 3 points are negative class. So, it belongs to the positive class. So, this is one pictorial representation of what I said. You make the neighborhood. In this neighborhood, this is the point which is to be classified, this is the point which is to be classified. Now, if you look at the neighborhood, exactly 3 are there. So, now increase the neighborhood little bit, increase the neighborhood little bit. Now, 4 points of this cluster 1 type. So, which means you will classify this to belong to the red cluster. Now, the most challenging issue in case of KNN is how to choose the value of k. If k is too small, the classifier will be sensitive to noise points, and if k is too large, the neighborhood might include too many points and decision making will be difficult. Next category is your decision tree. The decision trees are classifiers on a target attribute in the form of a tree structure. Here it has two kinds of node, the decision nodes in which the nodes in these nodes a single attribute value is tested to determine to which branch the subtree will which branch of the subtree it applies. Then in case of there is second category of nodes which are called leaf nodes, that indicates the value of the target attribute. There are many algorithms to construct this. So, these are few: Horn's algorithm, CART, ID3 and so on. So, this is one example of a decision tree. Here as I told you, there are two category of nodes, the decision nodes and leaf nodes. So, these are your decision nodes, this is decision and these are leaves. So, decision nodes and leaf nodes make this tree. So, while making these decision nodes, some attribute selection measure has to be used. So, this attribute selection measure, what it does? It splits the data set that best separates the given separates the data into two non-overlapping partitions. So, this data set D has to be now partitioned into two parts. Now, for the first partition, the next decision node is at this side of the tree, on the right side of the tree. For the second partition, so this maybe this is partition 1, this is partition 2. So, the data which was D here made two partitions. So, this from this partition, now this becomes the decision node, for this partition this becomes the decision node, and you continue till you reach at a point where you have all the leaf nodes, I mean all the data records has the same label variable. Let us say after this point you do not have to further partition the data point. So, there are three popular attribute selection measures: information gain, gain ratio and Gini index. As I told you, we are not going to discuss in detail. Now, during content based recommender systems, we will be using this such kind of models. So, when we discuss about those models in detail, that time when we use these models, that time we will be discussing this in detail. So, next category of classifiers are your Bayesian classifiers. The Bayesian classifiers provides a probabilistic framework for solving classification problem. So, it is based on the definition of conditional probability and Bayes theorem. The concepts of priors is very important, as they represent our expectation or prior knowledge which tells us about what is the true relationship among the variables. So, this prior knowledge has to be extracted from the existing data, and using this certain posterior probability has to be found out. So, there are two widely approaches for this. The first one is your naive Bayes classifier. In case of naive Bayes classifier, what happens? If you have a data set D containing a set of tuples with attribute x and a class variable, then if we have m number of such classes, it can be binary as well, m number of such classes, then given a new pattern, when a new pattern comes, what exactly has to be found out? Given the attribute x, find out which class it belongs. So, therefore, you take something called a maximum posteriori hypothesis. So, this tells to which class x will belong. So, x will belong to class C if this condition is satisfied. That is, the conditional probability of C I given x is higher than the conditional probability of any other class given x. So, now our aim is to find out, given a new observation x, we have to find out all these C I, all these conditional probabilities C I given x. So, once we find it out, whichever is the highest, the data will belong to that particular class. Now, coming to the Bayes theorem. From Bayes theorem we know that this conditional probability can be determined from this formula. So, which means for each of the C I we are supposed to use this formula. So, when we use this formula for all, then this P x becomes common. So, therefore, ultimately we need to know these prior probability values, that probability of occurrence of C I from the data and probability of x given C I. So, if we find and keep these values with us, then whenever a new observation come, we can find out these values. Now, again to make the life further simple, we assume that something called naive Bayes assumption, which is called class conditional independence. So, which means it assumes that there is no dependence among all the attribute values. So, which means when, because they are independent, we to find out these values of x given x I, we can find out x I given C I, then x 2 given C I, x n given C I. So, all these values we can find out individually from the data and multiply to get this. In case of Bayesian network, which also uses this the Bayes rule, we now connect the data points in terms of a directed acyclic graph. So, basically it has two components. One is a directed acyclic graph, this with, now in this particular example A, B and D are 3 variables and this is the directed acyclic graph. Now, with each node you have a conditional probability table. So, here D depends on both A and B. So, A can take 2 values 1 and 0 with this probability and B can take value 1 and 0 with this is the probability. So, which means whenever D is taking 1, D is dependent on A and B. So, A and B because both of this is one example in which we are considering the values of these individual variables are binary, but this may not be true. They can be any number of categories as long as we make these conditional probability tables. So, we have these combinations 1 1 1 0 0 1 1 1 0 0 1 and 0 0, and we already have these conditional probability values. So, whenever a new data point comes, we will be able to determine what is the probability. So, and when we use it for decision making, one of these nodes has to represent as the fine, because now see what exactly we are trying, given a data record x 1 to x p, we are supposed to determine y. So, all these p number of variables and y, all of them will be connected to each other through a network, and we are supposed to determine the value of y depending on what is the interconnectivity among all this, and by simply multiplying multiplying the corresponding conditional probabilities in this network, we will be able to generate this value. The second one, the next one is the rule based classifier. In case of rule based classifier, so far how many classifiers we have studied? We studied about tree based classifier, then we studied about Bayesian classifier, where we studied about naive Bayes classifier as well as Bayesian belief network. Now, there is another category called rule based classifier. In fact, these rules can be generated from both decision trees as well as naive Bayes. However, there are other ways to generate rules as well, but whatever may be the case, in case of rule based classifier, we have to have a collection of rules to decide the class. So, these rules have two things, one is antecedent, another is consequent. For example, in this rule, this is the antecedent and this is the consequence. So, this rule antecedent or condition is an expression made of attitude conjunctions, and the rule consequent is a positive or negative classification. Now, a rule can be assessed by its coverage and accuracy. Typically, from a whatever process you follow, whether it is decision tree, whether it is naive Bayes, you will be generating large number of rules. So, keeping all those large number of rules has certain computational implication as well. So, whenever you determine the class, you have to go through all the rules that is available to you. So, instead of that, you can assess the rules and keep few rules with you. So, what is this assessment criteria? There are two widely adopted assessment criteria, coverage and accuracy. This coverage is defined by n cover by the number of elements in the label data set, and accuracy is defined by n correct by n cover, whereas this n cover is the number of tuples covered by the rule R and n correct is the number of tuples correctly classified by R in the training data set. This artificial neural network, which in case of regression we studied as a mechanism to connect the input variables to some numerical variable, this can also be used as a classifier. So, how do you make it a classifier? You make certain additional step function, some kind of threshold function that can indicate the class. If the value is above a certain threshold, you say it is becomes let us say class 1, and below it becomes class 0, and this can also be extended to multi class classification problem, where you will have, let us say you have 5 classes. So, you will have 5 output node, and depending on whichever output node gives you the higher value, you say that the item belongs to that class, and it has to be trained, just like we discussed at the while discussing about the supervised learning. Again, some error function has to be minimized, and typically here the back propagation algorithm will be used or certain improvement over those back propagation, but error has to you have to compare the while training, you have to compare from the available pattern, you have to compare the output category with that of the actual output category with that of predicted output category, and you have to now iterate. This is a classifier which is different from all other classifier. How it is different from all other classifier? Because here in case of SVM, this support vector machine, in this case you have to remember some of the training patterns. How we do it? Let us try to see. Now, this goal of the support vector machine classifier is to find out the linear hyperplane that separates the data in such a way that the margin is maximized. So, this is a case, in here also you are separating, here also you are separating both the patterns, same pattern, but here in this context this margin of separation is much more than this. Higher it is, better separated both classes are. So, the idea is to find out to maximize this distance, to find out this is your optimally separating hyperplane. This is the optimally separating hyperplane, and this is your margin of separation. So, you have to find out this hyperplane, so that this margin of separation is maximized. So, you have to make some corresponding optimization problem and solve it. But while doing so, you try pushing these boundaries so much that some of the points will actually lie on this boundary on both the sides, and you try as much as possible that this as less number of points will lie on this boundary, and this there is in the formulation you can make certain flexibility to make this choice, like how to make it little bit this margin little bit flexible and decide how many such support vector you would like to, how many such points on the boundary you would like to keep. So, these points which are there on the boundary or near the boundary are called support vectors. So, these support vectors, as I told you, while you predict, when a new pattern comes, you have to suppose to predict the class, whether it belongs to this class or whether it belongs to this class. So, you are supposed to predict the class. So, in case while you try separating this margin of separation, some of the points will lie on these boundaries. So, those points are called support vectors. Now, your aim is to provide certain parameters, so that this margin of separation can be made flexible and you can decide how much to go and how many support vectors to keep. Okay. So, once you decide the support vectors and the model parameters, when a new pattern comes, unlike in other classifiers where you forget all the trailing patterns after the model parameters are learned, here along with the model parameters you are supposed to also remember these support vectors. Okay. Now, it may so happen that while deciding this margin of separation, some of the this is little bit overlapping and some of the patterns of this type are this side and some of the patterns of this type are this type. So, therefore, still then also you make the margin of separation, but you also adopt some kind of penalty, so that you may using this penalty you make this margin as wide as possible while taking care of these overlapping patterns. The second problem can arise when these patterns are not linearly separable properly. So, in that case you can use something called a kernel function. So, you can use kernel functions, so that you using the kernel, if you represent this data in terms of kernel functions, they are quite linearly separable. So, therefore, you can adopt the original method that you used in the kernel space and do it. In fact, you really do not have to do it, there are certain kernel tricks. Using these kernel tricks, you do not have to even go to the kernel space and do it. Using this kernel trick, you can have certain method to get this optimally separating hyperplane. So, these are some of the references I have used. In fact, most of the examples that I have used are either from this one or this one. In fact, I have followed the first reference as my guideline and prepared the lecture. So, these are some of the conclusions. Classification maps the input to a qualitative output represented in terms of nominal or ordinal scale. KNN, decision tree, Bayesian classifier and rule based classifier are used only for classification purpose, whereas ANN we saw that it was used for regression. Now, we saw that it can also be used for classification. In fact, decision tree also unless otherwise you can have something called a regression tree as well, which anyway we did not cover. So, then SVM we also studied about a new category of classifier which has to remember some of the training patterns. It is called support vector machines. So, with this we give a brief introduction took the classifiers in the supervised training setting. With this, we wind up this lecture. Thank you.